Welcome back to the channel. In this video, we are going to learn how to simulate the SG3525 pulse width modulation controller IC in the Proteus software. The SG3525 is a pulse width modulation controller IC widely used in many applications such as DC-DC converter and inverter circuit. This IC used to generate stable pulse width modulation signal with complementary output, making it suitable for driving MOSFET or IGBTs, half bridge or full bridge topologies. The SG3525 IC comes in a 16-pin package, and every pin has a specific role in generating and controlling pulse width modulation signal. Since the SG3525 itself is not available in the Proteus library, we will use a direct equivalent circuit IC in the Proteus UC3525. This IC in the Proteus has the same function and pin configuration. The pin function of the IC is described in the datasheet. For example, pin 1 and pin 2 used for the feedback and the regulation. Pin 5 for the CT, this timing capacitor, and pin 6 RT, this is timing resistors. This pin is used to set the switching frequency. Pin 7, this pin control the discharging of the CT and set the dead time between pulses. Pin 10, this is the shutdown pin. This often used for the protection circuit like overcurrent sensing. Pin 11 and pin 12, this is the complementary output of the IC. Pin 13 and pin 15 is connected to the main supply voltage, VCC. This supply voltage should be between 8 and 35 volt. Also about the pin 16, this is the V reference. This pin provides the regular 5.1 reference voltage. To build this circuit in a Proteus, from the library, select UC3525 IC and place it on the schematic. About the powering IC, connect pin 15 VCC and pin 13 VC together to 12 volt DC supply. Connect pin 12 to the ground. Now, add switch in series with the 12 volt supply so you can turn the circuit on or off during the simulation. Also, you can connect LED with the series resistor. This used as a power indicator. Place decoupling capacitor like 100 microfarad in parallel with the smaller capacitor 0.1 microfarad between VCC and the ground after the switching. This used as a filter for any voltage spikes and ensuring stable operating of the IC. To set the oscillator frequency, this frequency is set by the RT resistors pin 6 and the CT capacitor pin 5. You can set the switching frequency by using the formula in the datasheet. Increasing RT or CT will lower the frequency, while decreasing them will raise the frequency. Adding dead time controller pin 7, the dead time is the short delay between the complementary waveforms. This prevents both MOSFET from conducting at the same time. If we place resistor between pin 7 and CT the discharge time of the timing capacitor, which directly increase the dead time. About the pin 8, this is for the soft start to prevent inrush current when the converter first powering up. Connect a capacitor to pin 8. The capacitor value around 0.1 microfarad to 1 microfarad. Pin 9 is the compensation. Place a small capacitor 10 nanofarad to the ground. This helps stabilize the error amplifier loop. About the feedback loop, we'll use pin 1 and pin 2. Pin 1 is the inverting input of the error amplifier. It connects to the output feedback network. The IC compares this value of the pin 1 with the reference on the pin 2 and adjusts the pulse width modulation duty cycle to regulate the output. Pin 2, this is non-inverting input. The non-inverting input of the error amplifier, normally it's tied to the half of the internal reference voltage, approximately 2.55 volt. To get this 2.5 volt, connect two equal value resistors, for example 10 kilo ohm in series, between pin 16 and the ground. The midpoint of this resistors goes to the pin 2. Pin 16, this is the voltage reference. The value of this pin is 5.1 volt. This pin provides regulated 5.1 volt output from the IC. It can use to create the voltage for pin 2 and can also be used to supply other parts of the circuit. To absorb the pulse width modulation output from the IC, we'll connect the virtual oscilloscope in the Proteus. Probe pin 11 output A and pin 14 output B. We will note that the two signals are complementary. When the output A is high, the output B will low. About the dead time resistor, you will see a small gap between the both output A and output B. How to measure the switching frequency on the oscilloscope? To measure the switching frequency, place one cursor on the rising edge of the one pulse and the second cursor on the rising edge of the next pulse. The oscilloscope will show you the time period between these 2 points. The frequency is the inverse of the period. How to measure the dead time? The dead time, this is the gap between output A and output B. On the oscilloscope, place one cursor at the falling edge of the output A and place the second cursor at the rising edge of the output B. The time difference between these 2 points, that's the dead time. The SG3525 alone cannot directly drive large MOSFET efficient. So, to drive the MOSFET, we will add push-pull driver stage using the BD139 and BD140 transistors. This will make the MOSFET switch faster and with less heating. We will build two of this driver, one connected to the output A and the other will connect to the output B. Next, we connect the MOSFET in the push-pull arrangement with the transformer primary winding. The center tap of the transformer goes to the positive of the 12-volt supply, while the two ends of the transformer connect to the drain of the MOSFET. The source are tied to the ground. This way, the two MOSFET alternately drive the transformer. I hope this step-by-step tutorial helps you design your own inverter with confidence and give you a clearer understanding of how the SG3525 works in practical system. If you found this video helpful, please give it thumbs up If you're new to the channel, be sure to subscribe and turn on notifications so you don't miss upcoming video. Thank you for watching. See you in the next video.